Okay, so we're ready to tackle projectile motion now. You probably are thinking at this point that projectile motion is this really hard subject. Like it's this big green-eyed monster, and you're just this simple person who has to deal with it. But I want you to understand that in truth, it's more like this, where projectile motion is just a simpler class of, and a special case of, two-dimensional motion. So if you've already understood kinematics in 1D, and now we've added kinematics in 2 and 3 dimensions, projectile motion is a simplified case of kinematics in 2 dimensions. So what is projectile motion? Well, projectile motion is any object whose motion only experiences acceleration due to gravity. Now that should sound extremely familiar because that's what we said about free fall. And so projectile motion combines free fall in 1 dimension with, since it can't have an acceleration, constant velocity in the other dimension. Now, what sort of things are free fall, or are projectile objects? Well, bullets, water balloons, basketballs, baseballs, golf balls, footballs, meteors, stunt people flying through the air. There are just so many classes of objects that are just flying through the air without rockets attached, that as long as we can ignore any sort of air resistance, they are projectile objects. And so we can use projectile motion to describe them. If we were to make a graph of the motion of an object, and now this time it's not the motion in time, but in space. So x versus y. So just the up and down and left and right motion of an object. We might say a ball. We would expect it to go up and come down. If we looked at the motion diagram, we would see in 1 dimension we're going to have constant velocity, as we said. And in the other dimension, we're going to have constant downward acceleration, where that's might be the motion diagram as it moves up, and then, as we said, remember, as it comes down, a constant acceleration will look symmetric. And this means that there are certain things we know just because it's in free fall and it's in constant velocity in the horizontal direction. For example, we know that already the y component of our acceleration is going to be g, or minus g, depending on our coordinate system. The way that we've done it, where up is positive, then our acceleration would be minus g, where g is 9.8 meters per second squared. We also know that our final component of our velocity, the final component in the x direction of our velocity, is going to be constant. It's going to be the same as our initial component in the x direction. We also know then that the x component of our acceleration is 0. When we put our known values into our kinematic equations, we get the set of abbreviated equations you see on the left. For the y dimension here, you can see this is my constant acceleration equations. And for the x dimension, you can see I have a set of abbreviated equations because my acceleration is 0. And this is then my constant velocity equations. Now, one thing to be careful of, if you look at these equations, this uses minus g. Of course, this is because your book chooses up as its positive direction, and it talks about this in the book. There are cases where you might want to make down your positive direction, and then you would have to make sure that your y acceleration, or the y component of your acceleration, is g, not minus g. So it's minus g if your up is your positive direction. It's g if down is your positive direction. Now, some other interesting things are known when we look at the motion of a projectile. Here on the right, you can see the motion diagram in x and y of our object. Right, so I have my object, and you can see that it has some initial velocity. So all of these points are labeled with the initial velocities. The x components are also marked, and you should see that each of these x component lines are all the same length and point in the same direction. That's because it's a constant velocity. The y component, you can see, is slowly getting shorter, as we would expect, because my acceleration points downward, and so I should be getting shortening components in the y direction. Now, looking at this, something should stand out to you. Right here, this point should stand out. What do you notice about that point? Hopefully, you notice that it only has one arrow, and that is because at this point, the y component of my velocity is 0. This is where the ball reaches the top of its arc and it hangs for a second before it begins to fall down again. Now, the y component of the velocity is 0. The total velocity is not 0. In fact, we know what the total velocity is, right? The velocity is, in fact, equal to the x component of my velocity. And that is equal to the initial x component of my velocity, or the final x component of my velocity, or any x component of my velocity in between. There is at least one other interesting point we can talk about. If we look at the point directly across from our initial point, we also can notice some interesting things. For one thing, our x component is not changing, but our y component, this length, looks exactly the same as this length. These two components are the same length. And so we know that the y component of our velocity, when our object reaches the point on the y-axis, the same point on the y-axis, is equal to minus my initial velocity. In fact, you can do this for every corresponding position. Remember, we said how the upward motion is symmetric. As you go up, it slows down. As you come down, it speeds up, and it's symmetric. You can see this in the motion diagram. The y components of these velocities are all the same length when you connect these corresponding points. So we know then that at least if we come back to the same point, the final component of our velocity is equal to the minus the initial component of our velocity. Okay. That means, since our x component didn't change, the length of our final velocity for those corresponding points is also equal so that my final velocity, at least the length of it, right, the magnitude of it, is equal to the magnitude of my initial velocity. Now, I stress that it's magnitude because there is something importantly different, and that is the angles. The angle of my velocity has flipped across the x-axis, so that my final angle is now minus my initial angle when we're talking about angles relative to the x-axis. So you can see that just because we are in projectile motion, there are lots of things we know before we even have a problem, before we even start writing down values, before we even start writing down equations. We know a lot of things are going to be true. We know that at the top of the arc, the y component of the velocity is 0. We know that the initial velocity and the velocity at the end, if they're at the same height, will be equal. I stress again, they have to be at the same height. If instead our object hits some barrier, comes to this point, well, of course, at this point, our v final is not equal to our v initial. No way, right? Because those aren't corresponding along this horizontal line. So you do have to be careful. But if we come back to the same point in height, then we know that the velocities have to be equal. Now, before we finish our discussion of projectile motion, we want to define a couple more terms. The first one is max height. If we looked at our object, of course, we know that when it reaches the top of its arc, that's the highest it will reach, and that is the maximum height. Okay, so that our max height that's equal to the distance that we reach. Your book goes through a derivation of the formula you can use to find the max height. It is true even if we don't come back to the same height we started with. It might not always be useful, but it is always true. All right. The other thing your book defines and gives you a formula for is the trajectory. So this is the path that the ball follows. And it follows a parabolic path. The formula is in your book. It is equation 4.25. That one, again, is just taking your kinematic equations and mixing them together without any assumptions. The other two, so this then is the trajectory. And you can use that when it is useful. There is a formula for it. The other thing, the other two terms your book defines, one is the time of flight and the other is the range. Now, as you might guess, the time of flight is how long my ball is in the air, right? So this is, that's an h, how long the projectile is in the air. Your book gives you a formula for that. I, however, am not going to give it to you here because it is only useful in a very special case. It is only useful when I am on flat ground and my object starts and ends at the same height. When it starts and ends at the same height, then you can use that formula for the time of height or time of flight. But if it doesn't, if, for example, we stop at some other point, then that equation can't be used. The other thing your book defines is the range. So if I look at the distance along the x distance, then this is my range. So range is how far along the horizontal that I've traveled. And again, your book gives you a formula for that. But I will also stress that that formula assumes that you started and ended at the same height. If you don't, if you end up some other place, then you can't use that range formula. You'll have to go back to your kinematic equations and use these equations to find your range. Speaking of time of flight and range, we can see some interesting patterns arise. And these patterns hold true for almost all trajectories, even ones that don't come back or to the same height as your starting point. When we look at, say, the range, and if we were to look at what would give us the largest range, we actually find that there is a point on flat ground. It's 45 degrees, but there is an angle that will give us a maximum for our range. If we go under this angle, we will end up with a shorter range. If we begin to go above this angle, our range shrinks again until we come back to that same position. So that for complementary angles, supplementary angles, angles that add up to 90, you'll notice that when you look at this, we have a 15-degree angle and a 75-degree angle, and both of those ended up having a strike point or a range that is equal and much less than 45 degrees. Now I want to stress that those patterns are true only on flat ground. But you'll also notice that 15 plus 75 is equal to 90. So that complementary angles end up having the same, striking the same position in space. So you might rightly ask, what does the angle influence? If there's only a specific one that will give me a maximum range, what does the angle influence? Well, the more outward, so the larger I make my x component, reducing my y component, the faster, so the smaller time of flight I will have, the faster my ball will reach its destination. The higher I make my angle, so the larger I make the y component, then of course the slower, so the larger my time of flight. Notice that it reaches a much higher position. So this is longer time of flight. So if I want something to hang in the air, if I want a long hang time, I want to throw it high. If I want to get it there fast, I want to throw it low. Even though both of them may end up hitting the same point. If I threw a ball at 75 degrees and I threw a ball at 15 degrees, and I threw those balls at the same time, you would expect the 15-degree one to get there first. And that's it, really. That's all of projectile motion. Hopefully that wasn't too scary. As you can see, it is just a special class of two-dimensional motion. We've now talked about all the aspects of projectile motion that you need to know to begin answering interesting questions